Oh, you mean we were your wife? Or what?
Yeah, we are live.
Oh, we are alive already. Oh, I don't know. There's like this weird. What actually the live stream name that we ended up doing
Flux capacitor.
today? Yeah. So this is like very weird name. Very. It's not very the actual topic that we have prepared. It's just to clickbait people. But it's not like on the. It's not without any idea. It's just not on the idea of this quantum flux capacitor was the idea. We can try to explain it. It's not just from nowhere. There's some motivation to actually introduce this name. So I guess that's where we can start today by just introducing what this idea came from, and maybe just go from there, where this idea leads us, and maybe some other random ideas that I had this week. So that's why. So in our usual live coding like way. So
Okay, let's go for it. Sorry, I just got a brand new mic, so when we started the stream, everyone can only hear me now for the first time without background noise. So yeah, let's go back to. By the way, for those of you who are potentially millennials and do not know what this flux capacitor meme is about, this was a very culturally significant movie from the 80s, I guess, called Back to the Future. So check it out if you're curious. Very. This was a formative movie, by the way, for many of us. Apparently, there was a real flux capacitor invented in Australia. It was used for like electricity or something, but it wasn't a quantum flux capacitor. Hmm. Hmm. Can't hear Nick's audio. Nick, say something quickly. Just want to check your audio. Okay, yeah. Nope, no audio. Thanks, Dugan. Give me a second. Let's check. Okay, it says no, still not that. It's okay. Testing. Yeah, this happened last time actually. Testing. Oh, say something now?
hey, flux capacitor, fluxing. Hello, can you hear me?
Yeah, there's a bit of echo coming through from my side. So what I'm going to do is I'm going to do some background admin quickly to figure out how to avoid the echo, and then we can continue from here. You'll be able to hear me, and then the audience won't hear me for the time being. But maybe you can proceed with the idea here. What was the original idea of this in the movie? Was this a major prop in the movie? Was this what allowed time travel originally?
Yeah, I think so. It's like that's what Doc Brown invented. He like pulled up this tool or something like that, and he just popped into his head. And that's what allows time traveling. Yeah. Well, anyway, so the motivation for this kind of name, not particularly related to time traveling or anything, was just looking at this particular representation of quantum states in general. So now we have to go into actually working with our quantum framework, generate some random states, as we usually do, right? What I mean by a state representation again, right? In the usual conventional sense, it's just some complex amplitudes for your 0 or 1 or spin up, spin down. That's how you present, in this case, pure quantum state, or if it's like arbitrary mixed one, you can represent it as an actual density matrix. This is the elements of the matrix, but there are many, many other different representations mathematically equivalent to this. And one particular show, I don't remember any point, but here it is. It's like you have this property for the states called transition graph, right? And so what does it show? Let me add some labels to the edges. What it essentially shows some particular transitions from two conjugate pairs of measurements, right? So as the state is can be represented in different bases, right? You can convert your quantum state into arbitrary bases. Usually it's on a computational basis, either it's 0 or 1, which has some probabilities. There's also a conjugate basis that you can convert your quantum state into, like the X basis. This is the same as measuring in the Z basis. That's the probability of measuring either 0 or 1 for that particular qubit. That would be the probability of measuring it in the conjugate basis, like left, right, spin direction, for example. So it's a two conjugate bases that you can measure it, right? And those are the labels on this transition graph. So, and the labels on the edges completely describe the underlying density matrix, right? So you can actually think of those edges as some kind of capacity. That's where the capacitor coming from. You can think of those edges because in the network flow theory of graphs, it's usually called capacity. So that's why I borrowed it from there. So that some value on the edge can be assigned some kind of capacity of some potential value flowing through that edge. So that's the analogy, right? So if the value is negative, you can obviously naturally that would correspond to some quasi probability. We're probably going to explain later what it means, but when you represent it as some kind of direction of flowing, it's very natural to just invert all those capacity values that go into other direction, so that all your capacity of negative capacities can become positive. And that's where you can just invert those arrows and just draw them in the other direction, so that all the labels of the edges, all the capacities of edges are now positive, and you can read out all those probabilities of measuring the quantum state in this two conjugate bases from just following this flow of flux through those edge capacitance in this transition graph. So that's where the name is coming from. So this is like the flux capacitor representation of quantum state. So very catchy name. Okay.
Interesting.
So, and just to be more precise and concrete, how you can actually recover these probabilities from the flow, right? You can already see, probably guess. It's like if you want this probability to be computed, you just add all the flows, all the flux coming into this particular vertex, right? So it's like 0.33 and 0.31. You should give you around this value, right? Let's make it. So let's call it transition graph. In order to extract all the capacitance, what we call edge weights actually here, right? So at annotation value, transition graph, edge weight. So this is all the weights for those edges, but we want not all of them, but we want some particular vertices. For example, we just want for some specific edges that have one as a, well, let's just compute for all of them. First, we can like restrict all the edges that come through into any particular vertex. So for example, we can do it like this. Very weird. Oops. Directed. Yeah. So this is like just enumerates all the edges that come into all vertices, right? So this is like the edges that come into this particular vertex. This is the edges that come into this particular vertex, right? So we can just take this vertices, or just do it like this instead, and just ask for edge weights associated with this. So now we can just see all the fluxes coming into all of the vertices in this transition graph. So this is like how we extracted all the flux going into the one, or all the flux coming into 0, right? But we also need to subtract. Now we can total it. Now this is like shows the total, because like state number 1 doesn't have any outgoing edges, so it's already recovers this probability. As you can see, it's like the same 0.644. But for 0, there's also outgoing edge, so this probability is not yet correct. So you also have to subtract the same kind of thing, but you swap the edge direction. So now you extract the weights that not going into the vertex, but going out. Hold on. No. Oh yeah, that's correct. So that's how we recovered. It's just the excess actually recovered with the minus sign. If you want the change of sign, you can reverse all the arrows in the graph, and you can recover the correct sign for the x. But now the z basis is going to be with the negative probabilities. This is just shows that.
Sorry, just go one more time about how you got the minus signs one more time. How did you
the
get
minus
the
sign is just because we chose this particular orientation of the edges, so that we compute the probability by subtracting the outgoing from the ingoing, right? Mm-hmm. But because there's like this duality of bases, you have z and x conjugate pairs. For this particular graph, you compute in this way. You compute the computational basis like this, but for its conjugate, you have to reverse it.
Why is 1 the conjugate of x plus?
Well, because I call it a conjugate. To be precise, it means you have to compute the discrete Fourier transform. You can maybe, if you're really interested, so like computational basis is just an identity matrix, right? So this is like the computational basis. It has some matrix or elements. Let me actually show the association. Like this, 0 is just some unit vector, and 1 is another unit vector. Mm-hmm. So they form an identity matrix. If you ask for the x basis, it has some different representational elements like this. Mm-hmm. And those are related by the Hadamard matrix, which is just the 2x2 discrete Fourier matrix, how you convert one to another. Actually, you can construct one Fourier matrix of 2x2. It looks exactly like this, because that's what you get when you multiply it by an identity matrix. So in order to convert from this basis into this basis, you just multiply by the Fourier matrix. That's why we call it conjugate, because they form these Fourier conjugate pairs. It's like the same as in quantum mechanics, coordinates and momentum are related by Fourier conjugation. Okay. In this discrete case, z or y computational basis, which is what it's usually called in quantum information, which is the same as z, synonymous to it, is just labeled differently. It's just an identity, and if you want to compute its conjugate, you just multiply by the Fourier matrix.
Okay.
Okay. And that just shows how those two conjugate pairs related, which is the same as saying how the points in the phase space are related for this discrete setting. Because in the usual classical mechanics, statistical mechanics, phase space is also drawn for these conjugate pairs, like coordinate and momentum. Those are two conjugate parameters that you consider when you draw the phase space, and where particles occupy different volumes in this phase space. In this discrete settings, you just have 4 different values for all of it. It's like you just have 4 regions in phase space, which is where you just discrete chambers, so to speak, or rooms where your particle can live. But it can occupy, but technically occupies all of them like simultaneously because it's spread out across them. So it's not just a point, it's spread out across this whole just 4-dimensional phase space because just 4 different places that it can be simultaneously in a way. So it kind of flows between those.
But there is so is there a probability that it definitely exists somewhere within that space? I know this is like kind of the basics, but yeah.
There's no probability. Well, there's no definite anything, right? It's just there's like fundamental constraint that occupies the phase space, or like all of it to some degree, right? There's like if you consider some different states, like for example, if you actually have quantum state 0, which is 100% in this state, right? Which means you're completely certain about its position, for example, but you should be completely uncertain about its momentum. This means like this exact transition graph for the 0 state would look like this. There's like nothing flows into 1, or the edge there is 0, right?
But it is exactly 50-50. Yeah,
this is just 50-50. So if you compute the ingoing edges minus outgoing, here you get 1, probability 1 for measuring 0 state, and 0 to measuring 1.
So if this seems so elementary, why are people so like worked up about quantum mechanics? This seems like pretty straightforward.
Well, if you think, well, maybe it's like historically would have been like some complete different course of history. It would have been a complete different course of history if people formulated quantum theory, quantum mechanics in terms of quasi-probabilities and these flows instead of actual complex amplitudes. But I think, but maybe they would still invent the complex amplitudes approach because it's mathematically more convenient to compute actually. So it's just complex numbers make everything easier to compute. It's just the nature of computation. As soon as you can reduce something to a number that have more degrees of freedom, then it just makes life easier.
But I mean,
conceptually,
this isn't like a discrete version, right? There's no difference in discrete and continuous with this approach versus the complex number approach, right? It's just a different formulation.
Yeah, you can do the same kind of analysis. It's going to look much uglier in the continuous case because there's no like this nice graphical graph-like representation of it, because you actually have like a continuous phase space. So you don't have like an edge between every point, right? But here you actually have this representation. You can draw the arrows or this capacity between this conjugate pairs between momentum and coordinate. How the probability flows from one to another. Right. And from this kind of perspective, you can think of any evolution of a quantum state as just a rewiring of this capacitance, right? It's like some operator acting on a state. What it's actually doing is like plumbing these pipes, changing their capacitance and changing the underlying probabilities of how a potential particle would flow for them when the measurement happens. Some like this, you can recover this kind of interpretations. It's like you have this fixed structure. You can even think maybe it's made out of hypergraphs, hyperedges that encode this capacity of a particle flowing between the states, discrete states, right? And it's like evolution just rewires it, changes the capacity, but then when the actual measurement happens and people see a single outcome, not like all of them in superposition, it's somehow being amplified to the macro state by actually like throwing something into this, and it starts flowing. And if you do it multiple times, you recover the same statistics. That is encoded in those capacity and flows.
So just sorry
Because-
to go back just to the beginning here because I was trying to figure out the mic. Is there some what is the direction of the arrow? Why is the direction of the arrows important? Is that the negative positive direction?
Yeah, let me actually show where those numbers also coming from. Yeah, because the default one, because you want arrows actually going in from the conjugate basis to well, from some basis to its conjugate, right, in order to measure it. But sometimes the arrow is going to be negative because those actual numbers are coming from the usual phase space representation when you have the Wigner space, the Wutter's basis, and all that. When the actual probabilities are negative, right? In our framework, you can just recover those numbers by using the quantum phase transform function with a specific Wutter's basis, right? You recover the exact same numbers that you see in this graph as labels, as amplitudes in this basis, right? So that's why we have negative here. And what are those numbers? This is just like some basis transformation of underlying density matrix. You have density matrix, which is just 2x2 complex numbers. You can just do the linear transformation of those complex numbers so that all the complex imaginary numbers go away because of hermeticity of the density matrix, and you just recover just the quasi-probability vector instead. And this is the quasi-probability vector of this density matrix. And we just reinterpret it instead of having some quasi-probabilities, which we don't know how classically interpret nicely. We interpret it as fluxes between these conjugate pairs, because they naturally have this marginal property. When you just sum them up, you can recover the actual marginal probabilities for measuring in those bases.
What do you mean by marginal?
By marginal, I mean if you form this, you can also recover the same table like this, right? If you make a table out of these numbers, you should think of the rows and columns labeled by this exact states, right? So it's like a joint probability table. If you have a joint probability table, you can actually just make a categorical distribution out of this, I believe. I think you need tuples. Let's try to make one. No. How does it work? Should I flatten it? Hold on. How do you make this? Oh, because it's negative, it's confused. Right, you can't actually make a classical categorical distribution, right? But what I mean, if you could, you could take in this categorical distribution and just in order to marginalize over one variable, because it's a joint distribution over two variables, like in this the red variable and the blue variable. In order to marginalize it, you just sum up the rows, and you recover the exact same probabilities as we have, like where here.
Okay.
This one's right. So I recover just by marginalizing one of the balls, like the blue one in this case. Marginalizing means just sum over them.
Oh, okay.
Yeah, so I'm just summing over the blue variables to get the probabilities for red variables. If I sum up the columns instead, I marginalize over red variables to recover the probabilities of blue variables.
Okay.
So that's what I mean. And this minus signs goes away, right? So you recover the actual probabilities. So the quasi probabilities is just this underlying phase space quasi probability. All right. So that's kind of the picture for the. You can think of this as an alternative picture of the evolution of phase space, just revariant of those capacitance of edges, and you can think of measurement as just sampling from this graph flow network. You can also call it. I think there's this is the actual term in combinatorical science, I guess, combinatorial science of when people try to compute things like maximal flow for the network, given that the edges also have some capacitance, right? So it's a network flow network. So if you think of a quantum state as a flow network, and it can evolve with time, it can even correlate with it, like two flow networks can correlate with each other in some way, right? But when the measurement happens, something gets thrown into those flow networks, it flows, and the capacity directs this flow, and a single outcome can be recovered from that. It's not like solving all the quantum paradoxes, if you're wondering. It's because you still have this potential non-locality issues. Like, for example, as I said, you can correlate to flow networks, right? But if those flow networks are actually separated in space, what does this correlation actually means? It's like they actually have to be located somewhere in the same space in the hypergraph, for example. As the actual hypergraph, even though in space that we observe, they are separated by a large distance. In the hypergraph, they still have to be incident in some way so that the flow be correlated. Otherwise you can't really recover the same picture. Well, it's not unclear.
Yeah, I mean, we know there's not really a strict definition of locality yet, right? Or even like space.
Yeah.
But I mean, even in the real world, like it's all kind of like an opinion. But I've got a quick question. So this two bases. So does this mean that there's two bases for what you're doing here? Like 1, 2, 3, 4. Like this is a pair of bases. This is another pair of bases. Is that how you describe it?
Just two. Yeah. And it works like for multiple particles. Like here, the Bell state, your pair of entangled particles now shows two pictures, show two systems, right? So you still have two bases there, corresponding to all the momentum or coordinate of those two particles in this discrete setting. And that's how it flows for the Bell state, for example.
Okay, so I've got a quick question. This might be completely unrelated, but it's just got me thinking of something. So remember this, wait, just keep the thing still so I can draw here. So remember this thing that we discussed last time. Maybe I should discuss this at the end, but just so I don't forget, this kind of like makes me think that there's an even more minimalist version of the double slit which way path information. Because remember, like the thing I drew last time had these alternative like single things. But what I'm thinking is like you don't even need these to be able to say that there was some kind of negative possibility in terms of like probabilities going this way and then probabilities recombining. Just with 4 nodes in this network, you could actually have the potential for negative probabilities existing. So I was just wondering if maybe there's some kind of connection to the fact that there's this 2 base pair set up here and this minimal which way path kind of like splitting and joining situation happening in this thought experiment.
So the thing is that when you think of quantum state itself, like we don't introduce this many worlds interpretation in this until the measurement happens.
Until the measurement happens, yeah.
There's no like an entanglement doesn't introduce any splitting in the multi-way sense, right?
Yeah.
You don't have any alternative paths that you have to sum up to. It's just the whole state, even if it's represents multiple systems, evolves as the usual, like unitary transformation, whatever. It just evolves by changing the capacitance of edges, right? It can't be involved locally, like if it's like this system is correlated so that like the left system can travel onto the left and the right system travels to the right. And only local manipulations happen that change the capacitance. It still changes the whole flow through the network, right? It's like you changing the actual hypergraph structure that is not local, even though by changing some capacitance locally, you change the whole flow through the non-local network flow, flow network, even though it's like, because you create the whole flow network when the entanglement is created. As soon as the entanglement pair is created, this network is created. Then it's like if two particles travel at two opposite sides of the galaxy, if you locally manipulate one, you still manipulate the whole flow network that was created at the beginning, because they still have the same origin and this flow is still there. That's why it's like potentially so hard to actually maintain the entanglement, because you have to maintain the coherence in a way, right? Otherwise, you destroy this capacitance very easily and decorrelate your entanglement pair.
That's an interesting way of describing it. It's just a decorrelation. Like,
yeah, it's
like entanglement is like some kind of entanglement is some kind of non-local correlation. Sorry about there's a delay, so we're talking at the same time. But is that a correct way of like rephrasing it? Entanglement is a non-local correlation.
It is, yes. Yeah. It is you have like, even classically you can think of the like classical example of non-local correlation is like if you have two envelopes with some information that you prepare that they have some picture of a spin ups and spin down, right? You can correlate it and then send it to the opposite sides again of the galaxy. You obviously, if you open one up on one side, you know exactly about the information of the other because they correlated. So it's not, there's no information traveling. The correlation makes sense in classically. It's just that correlation has this effect of changing the flow through the whole network so that you can essentially for destructive interference to happen. That's the only non-classical effect that breaks this intuition.
Okay, I've got a quick technicality. So to entangle two particles, to have them entangled, they become disentangled when they interact with literally anything like physical.
Yeah,
or, right?
Don't necessarily decorrelate completely with some tiny interaction. There still can be weak interactions that don't destroy correlations completely, only weakly.
But it's wherever they're observed that correlation disappears. So if it goes through a polarizer, in the basis that the polarizer didn't eliminate, there's still a entanglement there. But in the direction that the polarizer disqualified or like created an observation or something, that part becomes decorrelated. Correct. Like if you have, like I heard that in an experiment you can have two entangled particles and then you can pass one through a polarizer, and then the correlation only exists in that direction between the entangled particles, like for the Bell's inequality for the CHSH game. So basically you have the particles that go, and then before you actually do the correlations between Alice and Bob, you pass one through a polarizer, and that like does have an effect. So the question is, the reason why it's difficult is that you have to maintain these states without letting it interact with like any reality, like any physical reality that's connected to the observer. In other words, there must be no information, right? So like even if it's like you as the observer, let's say you're the scientist, whatever, doing the experiment, it's not that you're necessarily seeing the result. It's a case that there is information about the result that now exists in the observable universe. It's like, even though it's difficult to disentangle, but there's some kind of remnant that if you had like perfect information about the experiment, you could figure out what the result is, right?
Quantum information in the sense of like von Neumann entropy is conserved, right? As soon as you it's a very fundamental law of nature, so that the quantum information is preserved. What happens when you actually measure Alice and Bob, measure their corresponding entangled particle, when the decoherence happens and destroys some of the information, it just leaks into the environment, but it's never destroyed. Yeah.
It leaks into the environment. I see. Okay. Okay, but it's kind of like it's destroyed in terms of there's a complex amplitude, or there's like a wave shape to the quantum state before it's measured. But when it is measured, it's the same energy, or it's the same amount of information. It's just now it's not a diffuse area. It's kind of like at a single point. Because it's 1 over
I
r,
lost
right?
you, man.
Okay, so I'm just thinking about like the formula. It forms a wave while it's in a quantum state. There's like this field of potential. But when you can identify a specific, let's say, momentum, then the potential for what the momentum could be, you've collapsed to a single number that you've now measured. Yeah. However, the position is still a field, right? It's still a set of probabilities.
Well, position itself is not a field. It's observable. That's the right way to call it. Right? The quantum states are sort of a field. It's just we're not doing any quantum field theory. It's maybe a quantum potential more than field. I'm not sure about that analogy, but yeah, again, when you measure exactly your momentum, when you know your which way information, as you like to call it, right? Exactly, then it means you completely disregard the information about the position. That's where the uncertainty principle comes from, right? Because you have this complementary pair of variables, even in discrete case. If you measure one, you completely don't know nothing about the other one, right?
So how's the quantum information preserved in that case? That's what I was trying to get at, because now you know something definite. Where did that information disappear to? How do you consider?
Well, because it's like diagrammatically, like let's imagine you have this state that you want to measure, right? This raw state. When you actually measure it, before you measure it, you have to entangle it to your measurement device or whatever, right? So, for example, the second wire underneath is going to be the measurement device. In order to entangle it to it, you have to, if it starts from 0, right? You have to, well, let's start it from plus, and then entangling basically means you have to do it like this, right? You have to correlate. You have to put some correlation between your environment, your measurement device, and your state that you're trying to measure. Right? This is the unity revolution. You do not destroy any quantum information, but then you technically discard your initial state, right? You trace it over. That's where that's non-unitary anymore. Right, you trace it out, you discard the information, but discarding is not unitary, it's not reversible, so it's still, if you should be technically considered another system, so that in order to discard it, it's like it removes the information. Every removal of information takes energy, so it has to go somewhere, right? But when you discard this measurement is now decoherent, right? If you actually evaluate it, you see that the metric, hold on, what I think I did something wrong here. The bell plus it should have been decoherent, but I didn't. So I did something wrong. Weird. Maybe I'm tracing a different basis or something.
The basis is weird different, but I thought that was deliberate.
Like my narrative breaks down. Hold on. my simple computation doesn't contradicts my claim. Hold on. Let's do it in the usual case. It's like when I measure it, directly and ask for the post-measurement state, right? It basically decoheres, zeroes out the off-diagonal components, but leaving the probabilities the same. So it's like this is the same. The diagonal terms are the same, right? But you zero out the off-diagonal coherence terms. They leak somehow. This information about those terms leak out to the environment. It's just what it means. I was trying to build the maybe just tracing out the different thing. Should I do this? Essentially, no. Okay, what's when I do the measurement diagrammatically like this in a very concrete manner, what I mean, it's like another way of doing it is just this, which produces the same measurement when you ask for the post measurement, right? But this can be further deconstructed as another way of simply doing is copying out the state, which is the same as correlating it to the environment. But then if you just trace out one of those, should be, yeah, this is decoherence. Well, why this is not the same as, I'm doing some silly mistake. This copying should be the same as correlating it. Let's do it on the 0, on the top one. Right? This is like the environment. This is the original.
Yeah.
This is just at the 0. So this is like, should be the same thing. And yes, I'm forgetting about something, I guess. Maybe I don't have to do Heisenberg. I'm confused. Why is it? I thought copy is the same as this, but apparently not.
So what is copying then? Because that orange thing that's connecting those two things, is that supposed to be entanglement? Or it's like some kind of
it's supposed to be. Yes, it's supposed to be the entanglement. Okay, what's happening? Oh, can't copy it. Trace on 0 doesn't work. Whatever. I broke everything. Oh, you can't copy like this. I changed something recently. Copy like this, right? To be more precise, like this is the environment, this is the state.
Wait, sorry, what's the environment?
Like, well, this system, whatever is here.
Okay.
On top.
Okay.
Like, this is just represents the same what I'm trying to do here by explicitly entangling, correlating it with the environment. Right? Like this relates to the correct decoherent state. But this one is not, which is a bit confusing. So for the
H. So what does H represent here?
H just turns into 0 into plus. So instead of, because this is essentially the same as also adding 0 there on the 0, right? Because I'm assuming that it's in the 0 state. I think it may be about. Yeah. So just, it should be conditioned. Of course, it should be controlled on the state. I don't know why I was doing it differently. Yeah, I don't know why. Like here, no, here it didn't work. Controlled.
Does it matter which way around it's correlated? We'll copy.
No, it should. Well, the ordering shouldn't matter. like this is the correct thing, right? But this and this looks to me, well, the plus. Oh yes, I don't know why I'm trying to put the environment into plus state here. It should be 0 then. Yeah, okay. I did figure out it then. Right, so what I was trying to do is just much simpler, even much simpler. Just what the measurement is pictorially, pictographically, is you control the environment. So you basically your actual state acts as a control. So you basically, if it's 0, then you apply nothing, do nothing to the environment. If it's 1, you apply the not gate. So that's what the control gate. In this way, you correlate your system to the environment, but then you discard it, right? And this effectively completely decoheres your state.
Completely, or just for that type of measurement?
Well, completely. I mean the actual decoherence terms, decoherence of diagonal terms becomes 0.
Diagonal terms, yeah.
It got projected on this line, whatever the block plot was for this, right? It was pointing somewhere there. Decoherence means it projects on this line.
Okay, but it still could be 0 and 1 now. There's still a probability distribution between those two.
Yes, exactly. So it becomes this. It's more likely to have 1 than 0.
So it's kind of like passing through a polarizer, right?
Yeah.
Yeah.
Exactly.
So that's my question. So now, does that mean some energy has, like the polarizers absorb some kind of energy? There was this potential there's like this energy potential, and then it hit it, and now it's leaked into the environment, or information's leaked into the environment. The polarizer like had some kind of interaction with that quantum particle, that quantum entangled particle. It touched.
Well, energy.
Like very small amount,
photon,
right?
It shouldn't change any energy of the photon. Well, maybe it's gonna change its frequency in a way, but it's still gonna be a single photon. As soon as it passes the polarizer, it's just in what direction its new polarization would depend on the angle, with some probability.
So the polarizer absorbs no energy from the photon at all.
Well, it depends on the actual physical device that you. I'm not an experimentalist. I don't know. You should technically lose some, maybe, but it's reflected as the frequency, right? As the photon. It's still a single one.
Okay.
Single photon.
Okay. Yeah. Yeah, that makes sense. I mean, the point is that there was quantum information, and that leaked into like it's kind of become classical after passing through the polarizer, a part of it. So the amount of information that the quantum particle contains is now less, right? Or not? Because we're trying to say
if the energy changed.
Yeah.
Well, the photon is like a completely different kind of particle that we are here. We only talk about the internal degrees of freedom, right? Not like anything related to actual momentum and position in space. That's where the energy.
Sure. So it'll more be like spin of an entangled particle or something like that.
Yeah, we only describe how spin changes if we focus on the internal representation.
Okay. Yeah, that makes sense. Okay, now I get it.
At least that's what we only care about in the quantum information world.
Okay. So quantum information is conserved, but doesn't that just tie into like energy conservation in general, or is there something more specific about the quantum information remaining quantum? Like that's what I'm saying. Like, isn't it just that energy in total is conserved, but the quantum information can leak into like just normal energy? like to the degree that
energy, energy as always can change type in a way, right? Even though it's conserved, but it changes like from heat to some field potential or whatever. Right?
So
the kinetic energy.
Yeah, so the quantum information can not be conserved if it's become decoherent. Are you saying for like I'm still trying to figure out in which scenario is the quantum information conserved? Like it's not conserved in all cases.
Well, the way the usual quantum information is defined in the sense of this value, right?
Mm-hmm.
Von Neumann entropy. This one is conserved. This is relates to, for the proper definition, what this entropy is. It relates to some extremal observable, right? It basically what would be the best, most informative observable measuring that state. What be measuring that most informative observable? What probabilities you would get and compute the Shannon entropy of that usual classical probability distribution. So it's kind of extremal, and it's just
okay. So it's like the amount of entropy is conserved.
Well, it's the same as saying that because the entropy is just the absence of information. So it's just some, because there's always a maximal entropy that the system can have. Like here is just 1 bit, right? The von Neumann maximum entropy is one bit, which is the entropy of the uniform mixture, the center of the Bloch sphere, has 1 bit of von Neumann entropy, right? So the information is just 1 bit minus this. You can think of it this way. The information of this state is 1 bit minus its von Neumann entropy. And that's value is preserved. Well, the fact that it's not pure, this raw state is not pure, is already an evidence that it's kind of is something leaked. It's the after state of some leakage to the environment.
Okay. Now I get it.
If you consider that the actual like universal state function is pure.
So is it? So maybe I'm trying to. Maybe the reformulation would be something like to the degree that you have these potentially different probabilities between the states, the combination of the probabilities has to be equal to the von Neumann entropy. Like you cannot increase or decrease it. It has to be conserved. The amount of entropy. Yeah.
Like concretely, you can like if you apply random, like just generating random stuff, it just shows the what you're trying to convey in the most easier way. It's like if you generate random unitary operator, right? If you apply it to the state, it doesn't. It changes the state, but it doesn't change the entropy, right? So that's how we can show it. If it's not unitary evolution but Hamiltonian evolution, you can technically like make some, take the logarithm from that and evolve it. Let me use the quantum evolve. It doesn't have to be just to be precise. What does it mean to evolve it? You have to put I in there, minus. Right, you have the parametric state, which is like time dependent. After 1 second, you should get. Oh, it's a different one. Let me fix one. So it's the same. That's the unitary evolution. Didn't change the entropy. This is the one that you do that you have. Is it 1 second? And show why it's not the same. But the entropy didn't change. Is it? Yeah. No minus sign there. Always forget. Yeah.
So it's evolved, but the states are the same.
Sure. Yeah. Well, this is like you can evolve states digitally, like applying a single gate. That's what quantum information quantum computation is all about. But in the conventional like evolution and quantum mechanics, you evolve states using Hamiltonians. That's what we constructed here. That's like Hamiltonian constructed from the unitary. And now you can involve it even not for 1 second, but for 0.1 second, for example. This is like one application of a digital gate transformation of the state. Is the same as evolving your state using a Hamiltonian for 1 second, right? We can even go further. And the Hamiltonian describes the actual physical system that you have, what kind of interactions of your system between, what is the interaction between system, how the system evolves on its own, how it interacts with some heat bath. You can describe by Hamiltonian general, and then it can even explicitly depend on time. That's what quantum evolve should also take into account, and then they actually have to solve the differential equation or solve it numerically. Yeah. Well, I forgot what we were talking about. I was talking about what was the definition of the von Neumann entropy, that the maximal most informative observable.
I thought you were going to go like, as you change the time, the states will change, but the entropy will remain constant.
Oh yeah. You can kind of see it. You can ask for this entropy. Can it even do it? It's kind of silly, I guess. If you don't remove the time, it becomes symbolically ugly, I guess. Compute this entropy. Well, we can do it like this is a parametric state. Can I ask for distribution? Now look at these probabilities there. Super ugly.
Can you plot that on a graph?
Yeah, that's what I'm trying. You can compute this entropy like this. Is it the same as von Neumann entropy? No, that's not going to be the. Yeah. You can do it like this. That's fine. Maybe. Sure, will it help? I just make a table. Oh, I forgot to ask for entropy. Yeah,
okay.
Doesn't change.
That you can plot. So can you plot that?
That's right. Let's move this thing. It'll make sense. The maximal, the most informative observable again. It's just it's essentially the same observable that is parallel to the state in the block sphere. So you can actually make a measurement operator out of the state if you turn it into, if you turn it into an operator, which is technically would turn it into an observable, and measure with this measurement operator the state itself. Then those probabilities, if you ask for the entropy of this guy, maybe not. I was hoping for this value. No, divide, because the entropy of this thing is actually it's in bits actually. No, it should be correct. Maybe that's not the observable.
Isn't the observable the states, not the entropy? Like you can't observe the entropy, right?
No, I mean the entropy of the measurement results. It's the entropy of these probabilities. So we compute the Shannon entropy of this measurement result. and you should get the von Neumann entropy if your observable is this most informative one, which I think is the same as, but actually is not. I know how to compute it using just the block vector explicitly. Maybe.
Is the operator here like the person doing the experiment?
No, in a way, observable is what the observer defines his measurement. It's like he defines the measurement measures what kind of measurement he performs.
Okay.
So it's
the measurement basis.
Yeah.
God, sorry about that. I was right next to the microphone.
Yeah, I don't know. I was sure that it should be the same.
Let's make that as a question to come back to. How do I define the question? Yeah.
How to compute the most informative observable.
How to compute.
So then I actually should have it somewhere.
How to compute the most informative observable. Observable.
Maybe an observer also makes sense. I think I had some notebook about it. Here. It's even called most informative observer. Hold on, let me.
Oh, that arrow escaped the blocks here.
Yeah, because that's not a state, that's an observable. It's allowed to do it. It's because it's you define the eigen. It doesn't constrain by it. It's just you technically can plot it.
This is like this little ball is kind of like my actual visualization of what happens with like quantum spin. So basically, you have this boundary. I know it's not a correct analogy, but I'm just saying like visually, it looks like how I think about a quantum entangled particle, where you have this boundary that you're not allowed to observe inside. You're not allowed to like pierce this veil of quantum state. And as soon as you do, then that's like what collapses the quantum like probability density. So that little block sphere is like a nice way to visualize how I think about it.
That's the answer. Just the wrong basis of probabilities we were considering.
Okay, so this means that observers are computational. So doesn't that just mean that these quantum formulas has now proven the Wolfram Physics project correct?
Well, that's not the only point of the Wolfram Physics project. That observers are computational. It's more like just the underlying foundations that everything is computational. So, sure.
So if we could just get this to give us general relativity, then boom.
It's just not in this sense computational. This means just the basis change. Yeah. Maybe you just seen that it's computational, right? Well, yeah.
What is your theory about how we could get gravity out of quantum mechanics? What's your best? Your highest probability
out of quantum computation itself, or just in the Wolfram Physics project?
No, just like unifying the two. I mean, the physics project is the substrate with which you could potentially get the formulas to agree, but based on like the actual formulations, like quantum field theory and general relativity. Even if we did it through raw maths or in a computational way, How do you think they would? How do you think we could get them to agree?
Well, they would agree automatically as soon as you, for example, consider these both pictures. We already have a good representation of the relativity in terms of computation as just events and their causal relationships, right? You just have to clarify what are those relationships are. So in order to explain everything quantum too, right? And if you, for example, what we've talked today about those capacitance and this particular representation, those could be one source of that relationship. What kind of events those could happen in this computational substrate that you're trying to evolve, right? Because you evolve, in this case, you would evolve those capacitance, which can be represented more fine-grainedly as an actual hypergraph or whatever, right? You evolve this particular structure. Then from it, other computation produces a measurement outcome, and all of those correspond to some kind of actual events. Because a unitary evolution, one digital transformation of those underlying states is one particular event. You evolve this, you construct the causal graph, and that's from that particular structure you recover all the relativistic properties. So it's very naive. It's not like I don't myself believe in it too much, right? But
is the biggest hurdle there getting that negative arrow into that formula?
No, I don't think it's very. There's no conceptual problem to it as soon as you allow for this non-local hypergraph interaction. Well, not interaction. The interaction and rewrite rules are still going to be local, but those connections that don't evolve too much, right? So that you technically allow for
foliations of time
events to be very spatially disconnected, but even though the actual inputs on the hypergraph are very almost incident to each other, or very close, right?
But still, how do you get the negatives then?
Well, that's just in the encodings, right? It's whatever you, because rewriting is universal. You can do whatever rules you want. You can do it universal Turing machine. It's just about how you can represent it more.
It's how the observer is going to represent it using their internal model of the observation, right? Those will have those will have a model of mathematics that allows for negative probabilities. Kind of. Isn't that sort of what we discussed last time? It's the fact that however the observer decides to model it, the observer will have a mathematics that makes sense with negative probabilities. But in terms of the underlying computation, you don't have to literally introduce negative pathways. That's just the way the observer will make sense of it.
Yeah. Here we don't even introduce the pathways, like in any like path integral formulations and all that. There's like a single path of evolving paths in a way. You have a single way path evolving space-time, which evolves this potential flow distributions that can manifest itself when the measurement happens. But those pathways, they can be distributed in actual space, not not very naive way. It's like they could be non-local, even though events can be very space-like separated. But on the hypergraph, there.
I mean, that's the concern with the CHSH game, right? That's the concern with Bell's inequality, is the non-locality. Like the weirdness comes from the non-locality, but there's other experiments you can do where the weirdness shows up in different places. Like the double slit experiment has the weirdness in the interference pattern. Schrödinger's cat has the weirdness in like both states existing at the same time. Yeah.
Well, for some people, it's not weirdness. For some people, it is. It's just about the nature of paradoxes. So as soon as you try to actually explain it, that turns out there's no paradox, right? As soon as you formulate it clearly.
The narrative contains the paradox.
Yeah.
That's a good way of putting it. So the quasi-probabilities exist in your head.
Yeah, that's in the model. what we're trying to describe. That's the mathematical formulation requires it. But if you have this, if you want to build this computational model of it, that's how one way of interpreting it. You have to still bend down under some of the violation. You have to believe in one type of violation. In this case, you assume non-locality. But in the specific case, there's actually good non-locality in a sense. It's allowed. There's no contradiction with the physics project and all that.
Yeah.
Still fine.
Where are the quasi-probabilities? They are in your head. Where are the quasi-probabilities, Nick? Are they in the room with us right now? No, they're in your head.
No.
It's so true. It's like, where are the negatives? Like, how do you have a minus 1 pen? Like, it physically is impossible to have minus 1 pens. But in my head,
but you can do. But you can flow in a backwards direction. It can be even some backwards time direction in a way.
Yeah, over time the negatives make sense, because now there's a plus 1 pen, now there's a minus 1 pen, but only with respect to a second ago, you know. Yeah. So that's like measuring speed. It's like if you didn't have a good enough time lapse to be able to determine at what point there was a pen or there wasn't a pen, the pen exists simultaneously and does not exist simultaneously. But that's like more like 0 and 1. It's not a minus pen, because the states here is 0 and 1. It's not 1 and minus 1.
Well, those states can be anything. It's like this is like interesting asymmetry between states and observables, right? Because you require, in the quantum theory, you require for states to be positive in a way that its eigenvalues has to be positive and between 0 and 1, so that you interpret them as probabilities. But for observables, you require the exactly same conditions for it to be Hermitian and all that, but you don't require this positivity from the observables, because those eigenvalues are you actually interpret as some physical observables, like energy or spin. It can be -1, minus, or any kind of energy level. It's whatever you observe physically. So it's when you compute the expectation value. Right? The expectation value, in a way, you average out your eigenvalues, the observable values, with the probabilities that those values can take, right? Appear in those values. And they kind of, when you average them out, they symmetrically,
your expectation values. I like that framing of it, because that ties into entropy from the observer's perspective, because an observer has a certain amount of expectation, which is informed, which the entropy kind of like affects.
In this case, it's just a mathematical term. It's like an average, the expectation value.
It's the average of what? All the possibilities.
All your possible outcomes.
Yeah.
Right? -1 spin and +1 spin. If they happen with different probabilities, the average can be anything in between.
Yeah.
Right. And because they're like symmetrically like written in this expectation value, probabilities and values themselves and the outcomes, they even evolve in a similar fashion. Like if you evolve a quantum state, which is the probabilities and the expectation value expression, you evolve it like in forward direction using the Hamiltonian or whatever, but you can do the same kind of thing. Instead of evolving as probabilities, you can evolve the expectation value, but backwards in time. Right? It depends. That's essentially the difference between the Schrödinger and Heisenberg picture of the quantum mechanics. Right?
Explain the Heisenberg picture. Does he have a nice visual paradox to describe his version of it?
Well, the difference is just what evolves with time, right? Either you evolve the state or the observable. That's the only difference between those pictures. the Schrödinger picture in a way won in the heads of the physicists, because it seems more natural to evolve the actual state, because that's what we typically describe. It's like, here's the system, it evolves with time. Makes sense. But the opposite thing, to evolve the observable, it's like evolving our interrogation technique of that state with time or whatever. It's a measurement device is being evolved instead. It's like, it's not very natural, but that technically, mathematically, they're just opposite to each other. You can perform one or another. It's just in a different direction.
Is it? Could you say that the same way that spin and momentum are kind of like in some kind of like quantum state, that instead of spin and momentum, you have like time and something else, and those things are in a quantum state?
Ask it again.
So, you know, like spin and momentum cannot be measured with perfect precision at the same time. So is the Heisenberg picture kind of saying like time and something else are in a quantum state?
Well, first of all, like momentum and spin, they can be measured, I think, because they're not conjugate pair. It's coordinate and momentum. But
coordinates and momentum. Okay. Spin and momentum. Oh,
there's
sorry.
There's another canonical conjugate pair. Is you have momentum and coordinate. You also have time and energy.
Time and energy. Yes. Okay.
Yeah. So those are also form a conjugate pair. There are much more problems with it, though. It's like, because they don't form, at least time doesn't form an operator, right? Even though you can form operators, you can make an observables out for position and momentum. You can't make an observable out of time easily. So there's some resolutions to that. Yeah, but it's not like as direct. Well, I'm not sure. I can read about it. I have it in my to-do list to understand why the time observable is so complicated to construct in quantum theory. But it seems like there's some papers that have some solutions to it.
Okay, that's interesting. So wait, going back to the Heisenberg interpretation, is it fair to say Heisenberg interpretation of quantum mechanics? Is that like the correct name?
Yeah.
Is there the analogy of the cat in the box with the Heisenberg interpretation? Is it like a clock on a train or something? Like, is there like a thought experiment that's easy to use for that?
I don't know. Maybe you can. It's just maybe that's why Heisenberg is not so natural, because this kind of formulations is much harder or non-natural. Because it's not like what you describe your evolution of the system, right? Not the evolution of the observable usually. It's like when you describe the situation of a cat in a box, you already assume that you evolve in the state, not how you would measure this the state and observe the cat.
Okay, I'm going to chat GPT this quickly. While I'm doing that, there was something that we mentioned last time that I wanted to know if we figured out here. So there's negative. Was this what the main thing you wanted to show, right? This what are you calling this, by the way? Are you going to literally call it the flux capacitor?
I don't know.
Quantum flux,
we have like this transition graph name. It's boring name, but that's what we call it. We can call it flux capacitor just for fun, but yeah.
So I guess the reason why Schrödinger's kept one out is because Heisenberg's interpretation didn't have a direct analog in terms of a thought experiment. Heisenberg's approach focuses on observable quantities and their relationship through matrices. So
yeah. It's a mathematically equivalent picture, but didn't want as an interpretation picture.
Yeah. Schrödinger's cat just makes it's easy to visualize. It's the more tangible visualization. I wonder if would it be worthwhile to try to figure out what a thought experiment could be for the Heisenberg interpretation as like a physical experiment?
Well, try it. Like, how would you, as an observer, open the Schrödinger cat box
So
in the opposite direction? It's
okay,
like
okay. So let's
first you observe the cat, then the dying happens. I don't know. Then the whatever the atomic nuclei they're radiating it happens after you open the box. It's like you have to trace back the steps because it's you consider the process is reversible, and you
okay,
basically trace back your steps of measuring instead of evolving over nucleus radiating, triggering the some poison vial, and the cat dies.
Okay. So that's the random variable. So the random variable, the entropy in the Schrödinger's cat example is this nuclear decay, right? The particle having some kind of decay moment. So it's almost impossible to predict when that will happen. So that's your random variable or your random parameter. So what you're saying is the Heisenberg interpretation, it's not that the state of the cat changes over time. It's what something else is changing. Is that what you're saying?
Well, the observable is changing.
And what is the observable? Maybe we need a good definition of the observable.
Is you opening the box.
You opening the box.
Whether the cat is dead or alive.
Okay.
Right? It just doesn't make sense to evolve it because after that it doesn't. It's like changes to not opening, not observing the cat, but observing the poison, right? And then observing the decay. That's kind of the evolution of the observer.
Okay, so how about we do this, right? There's a cat in a box that we don't know if it's dead or alive from the perspective of the observer outside of the box. So the nuclear decay triggers the time at which you decide to open the box. So the random variable is the moment in time with which you open the box. But the cat, if it stays in the box, it's going to die eventually, right? It starts off being alive, otherwise it wouldn't be a cat. But the point is, at what time do you decide to open the box? You see, so you evolve in time with a random parameter from the perspective of the observer. Because in the Schrödinger's cat example, it's like at this time, at t equals 0, you open the box. What's random is whether the cat's dead or alive. Maybe in the other way around is like what's random is the time at which you decide to open the box. But the cat's going to start at 1 and it's going to end at 0. But somewhere in between, there's a probability distribution, and it's going to depend on at what time you open it.
No, that seems too convoluted. It's okay.
Is it correct though? It might be convoluted, but it's
like you have a random variable. Yes, it depends on time. That's how you the decay, the change, this particular one, the first interaction in the box is random, but you don't want to evolve that. It's like you kind of fix it.
Mm-hmm.
Times you will have this snapshot of your experiment at the beginning. Instead, you trace back from your potential observable back in time what kind of events should occur. That's just the mathematical device in order to compute your expectation value. It like doesn't make sense to even build a narrative around it, or at least it's too complicated. It's just like a mathematical device how to compute like your expectation values. In this case, expectation value is like the average of your dead and alive cats. So it's kind of in order to describe one instance of an experiment and this kind of things being in superposition, it doesn't even make sense in the Heisenberg picture. It's just it's unless your observable is in superposition now, you just don't.
Okay, so there's two. So in other words, I'm in a superposition of opening the box now or later. And
it's not now later. It's just your time behaves in a similar way as in the Schrödinger picture. It's just in the backwards direction. You already have.
You've already opened it.
You have time dependence on the random event, random time when it happens.
Okay.
Right? Whether it happens or not. You can just a binary variable. You don't have to think about time at all.
Okay.
Right? It's just a random variable, like maybe 50-50. Your state changes. So in the Schrödinger picture, you describe it as a superposition. Right?
So is there not a superposition of observers in the Heisenberg interpretation?
So it's like in terms of a circuit, it's like it's just an exercise of building narratives around weird things. It's like if you have a quantum state 1, which is your alive cat, right? It's a happy cat. Where's my cat? It's happy.
Okay.
Right, here it is.
Yeah.
The breakage of the poison with 50-50 probability just apply the market. Because if this one in the Schrödinger picture, it's now changed the base, which actually make it in the same one, just to make it fun. I'm gonna make a cat basis. Like that. It's the other way around. This this is in cat basis, and this is in cat basis. Okay. There. Here it is in superposition sort. Okay.
So what's H here again? I keep getting confused.
No, that's just think of it as just creating the superposition.
Okay.
It's just random 50-50 chance now, right?
Okay.
So instead of applying this gate, is the same. Now we want to do the same kind of thing backwards.
So is H the poison gas?
Yeah,
or it's the particle decay or whatever it is.
It's all of it in combination. It's just your decay happening with 50% of chance, triggering and joining your cat in one of those states.
So can we change the H to like a particle or something? Like, would that make sense? Like the emoji, the H.
I don't know. Oh, it's not even rendering. That sucks. Not all emojis are working, I guess.
There was one there with like toxic or poison or something. Yeah, that works. Okay.
Oh, good. Let's make it big.
Okay, that makes more sense now.
Now, I guess we also need to create a measurement, an actual observer. So let's create an observer with the measurement. And it also measures this. This just measures the cat. Don't worry about this. How it looks like, but this is. Let's see. Let's add the label. Some professor. I have some professors, some scientists. That guys. Let's do this. Yeah. Doesn't work. Notebook is not liking all emojis for some reason.
Maybe it's Maybe it's where it's two emojis together. Like some emojis are just encodings of two standard emojis. Yeah, that looks like a magnifying glass or something.
That works. Okay, so here it's here. Observer. Okay.
Mm-hmm.
So that's our experiment. We code like this.
Mm-hmm.
When we run it, get some 50-50 probabilities of measuring a cat.
Mm-hmm.
So what does it mean? So now the point what we want to do the same kind of thing but backwards.
So the observer is in a quantum state, a 50-50 probability.
Yeah, well, when you said this observable, I took it just like this observer. Now, wait up. Instead of using the basis, we can actually make it into. How do I make an operator? I just need to make a projective observable. Instead of using cat, can make z. That's going to be an observable. Like this. It's going to be this. This. Same thing. Now the observer is this projection operator, observable rather, right? We can treat it as a state. We can turn it into a quantum state, which looks like some mixed state of cats in this case. It's just like if you think of it as an actual observer, it's like it represents an uncertainty about the state of the cat, right?
Okay.
That's our initial observable. Or state of observer. Now we have to evolve
of the
it
observer. Yeah. Okay.
So we only have a single gate here. The only thing happens. Actually, it is the same as in one direction as another direction. I think it's you take the dagger. That's the reverse of it, and they're the same. So it's very easy because our inverse operation is the same. So okay, let's try building circuits. So now your circuit operator starts with this observable state. Let's give it a name, I guess. Like the observer is not maintained. Oh, that loses its label for some reason. Oh, let's give this. Let's give it the label. Maybe I should have given.
So it's time reversible. That's the important thing. So it's not that you can create a random variable from time, because the point of the Heisenberg interpretation is that time is not a factor. Is that what you're trying to say?
What?
Oh, sorry.
Yes, it's not a fact. Yes, it's not a fact. It's just our. What is it? Observable. Yeah, the state is not.
We're building a time machine, exactly. That was not the intention of the stream. That was supposed to be clickbait, but now we're actually building a time machine. We're keeping time constant. We're trying to figure out how to keep time constant and absorb and evolve the observer.
The time constant.
Oh, it's not right.
It's kind of it's still
reversible.
Evolves, right?
We're making it reversible.
We're just doing it backwards in time.
Backwards. Well, the DeLorean went backwards and forwards in time, right? So.
Well, I can go forwards in time any moment. Just not too far.
Good point.
Okay. So we again apply this technically a dagger of this Hadamard, but it's technically it will be the same. What we're going to represent, we're doing it backwards.
Okay.
Right?
Okay.
And then there's just a cat, which wasn't the in the known state, right? So it was alive.
Mm-hmm.
No, it's not the basis. When we made the actual cat here, this is like a definitely a live cat.
Sorry, wait, go a bit slow. I'm trying to catch up here. So
it's like we're doing it like this.
okay.
And that's how we compute the expectation value, I guess, of measuring a cat. And we should just get a single number. Like this is now just computes the expectation value of a cat being dead or alive, and it should be just what 1 how 0. Why is it 0? No, because maybe evolution doesn't make sense in this case, right? Because we evolved the observable here.
But what's evolving the observable? Doesn't an observation have to be made in order for evolution to occur? Because you're taking the measurement device out of this quantum circuit.
Observe a cat either in the box. So,
but something
it evolved by the setup.
But something has to happen to the observer for time to change. So time's not changing. Yeah. What's changing? The expectation? The expectations are changing? Hold on. ChatGPT has tried to adapt the thought experiment to the Heisenberg's interpretation. Should I read it and then see if it makes sense?
I'll try.
Okay.
Sure.
So there's a setup and there's 5 steps. So the setup is a cat is placed in a sealed box with a radioactive atom, a Geiger counter, a vial of poison, a hammer. Okay. The decay of the atom triggers the Geiger counter, which releases the hammer to break the vial and kill the cat. Okay, that's like the standard setup. So the quantum state in Heisenberg's matrix mechanics, the quantum state of the system is represented by matrices. The possible states of the atom, decayed or not decayed, and the corresponding states of the cat, dead or alive, are described by matrices that evolve over time according to the Heisenberg equation of motion. So far, is that correct, or has it already gone off the plot there?
No, it is. It's just not very instructive.
Okay, then observables. The focus is on observable quantities, like the position or energy of particles. In this case, the observable is whether the cat is dead or alive, linked to the state of the radioactive atom. Measurement. Prior to measurement, the matrices representing the system's state contain probabilities for all possible outcomes. When an observation is made, opening the box, the matrices collapse to a single state, revealing the cat is either dead or alive. Uncertainty principle. Heisenberg's uncertainty principle implies that certain pairs of observables, like position and momentum, cannot be precisely measured simultaneously. In the cat scenario, the precise state of the atom and thus the cat is not determined until a measurement is made. Interesting. Okay, so that's tackling from a completely different way to what we're doing here. Isn't it just that Heisenberg's uncertainty principle? Wait. So is this just Heisenberg's uncertainty principle? Is that what this is?
No, we're not.
Oh.
We're not trying. Like we're trying Heisenberg picture of the evolution of that scenario. Instead of evolving the cat and the state, we're trying to evolve the observer, the observable. Just trying to make some sense of this representation for this scenario. That's all we're trying to do, not anything related to the uncertainty principle. So yeah. So Heisenberg confused GPT there because he has an uncertainty principle and the picture.
Okay.
And the matrix mechanics of observables.
Okay. But is there some kind of relation to quantum states and uncertainty principle? Because the position and momentum is in some kind of quantum state. or not really? Is that not necessarily the right way to think about it?
But they're in a sort of quantum state. It's just quantum state contains the probabilities, but observable is the projection of the state into one of the concrete values for that observable, like an actual coordinate or position, coordinate or the momentum, right? The actual values of those things, not the probabilities of those happening. So you can either evolve the values or you can either evolve the probabilities.
Okay. Now I see what you're saying. So the other way of so normally we evolve the state. Here, wait, no, normally we evolve the probabilities. Is that what you're saying? That's the standard way of doing it.
Yeah, the Schrödinger way.
Okay, but here we're trying to evolve the states. The
states are probabilities. The states already describe your probabilities, and like the states are those pipes, whatever. The states are describe this picture, dynamical picture in a way. They describe how potentials evolve. The states are potentials, they evolve, and they describe what would be the probabilities when you actually observe this. Right? When with a fixed observable, you have a fixed observable in time, and you evolve this picture, you evolve this pictures with time, and then you apply the fixed observable. You can do it the other way around. You start with a fixed potential of probabilities that can evolve from, but you evolve the values or whatever. If you have this weird analogy as if this is the actual pipes with something flowing between them, and you can throw some paper boat or whatever that flows there with some probabilities into different directions. What you evolve, you either evolve the pipes with those how they correlate and diverge, or you either evolve the position of the boat. It's like not the position even, the actual because you assign some values to it. Maybe you always throw it and it's like in this conjugate direction in the momentum box, but the value would be different. So it flows. You throw it always randomly, maybe, but the actual value written on the boat is different. It's like and it depends when you actually read the expectation value or the actual value that you. Because only the device for computing expectation value. That's why the narrative breaks down of evolving the actual values. Right? You can't really evolve. Maybe you can. It's like instead of having spin up, spin down, like for it to evolve to something like a spin minus 3 or 5.
Wait.
If it makes any sense at all, in order to reconstruct because only average matters.
The average matters because measuring all the different, like running the experiment multiple times gives you different outcomes, and then taking that average gives you the probabilities effectively, right? Yeah.
You can also think instead of an observable evolving, you can also think of it as basis evolving with time. So that's what is being changed.
The basis is evolving.
But basis is just you think of the basis as a set of questions you ask of yourself, right? So either your state evolves, or either your and as I said previously, like this interrogation technique changes. But what is your set of questions of your system would be?
To open the box or not to open the box? That is the question.
Or with what probability to open it? Like you set up. Like in that old stream we did about the coins. Remember when I said that you can specify a basis with the 2 set of coins and measure with this basis. Right? That defines a set of like a question about your biased coin. You have arbitrary biased coin that can land either heads or tails with different probabilities, right? And you kind of ask a question by using a different set of coins. Instead of head of tails, you use some linear combination of those and form a different question. It's like maybe it doesn't make sense, but operationally you can do it with the statistics and throwing it a bunch of times. You can determine those probabilities in any basis.
Mm-hmm.
And then sometimes it's like that wouldn't even make sense because even this simple picture you get negative probabilities if you choose bad questions to ask. Right. So if you think of basis or observable as the set of questions, that's what's evolving backwards in the Heisenberg picture.
Why is it evolving backwards again?
So because you ask the question at the end, so it's like right. It's like if you have a circuit, you either evolve the state from left to right, or you evolve the observable from right to left. In order to compute the exact same thing, you just do it in another direction.
Okay. So, but isn't the outcomes on the right the answers to the questions, or are those the questions? The observers asking the questions and getting the
observable operator.
Okay, the observable is the question. The observation is the answer.
The outcome, yes. The outcome of the question. Or the single instance of that.
That's cool. It makes sense. An observable is the question. An observation or an outcome is the answer. Okay, I'm taking some poetic license here a little bit. But the point is that what question you decide to ask you can have the same outcome, so you can have the same answers, but if the question changes, it's going to make sense in different ways, right? Like you could say, what's 21 times 2? Or you could say, what's the meaning of life? It's the same answer, but the basis for your question changed.
Yeah.
Right?
And, no, I don't know what to trying to describe here, that there are different questions. The questions, yeah, the questions take different form, but when the revolution is fixed, right? If you change the process of how evolving happens, either or state or observe or the questions, you don't like ask the different kind of questions of the same state in this way, right?
Okay. But if they're not different questions, then how did the questions evolve? How did the observables change?
No, it's like a binary question, yes or no.
Okay.
Right?
Okay.
It can evolve, like it can start with this completely 50-50 type of question, yes or no. But instead it can evolve just like to what degree it is yes, right? Is it like, are you sure that's like 80%? Well, it's a weird way, but quantitatively you can do it, right? To kind of nudge the probabilities of that question. It's like you kind of bias towards the yes answer in some case.
The yes answer or the so I'm trying to think like what it means to evolve the observables. Wouldn't it be a case of like, let's say there's 4 potential things, so you can ask a question yes, no, up or down. That's like your observables. But now how you evolve the question is like you might say yes, no, or up. You say yes, no, or down.
No, your outcomes may be fixed, right? But it's some quantitative things it's changing. The probabilities of those, like the eigenvalues of your questions, are fixed technically.
Hold on. No, let me draw a picture here quickly. Hold on. Let me make some space. Okay. So what I'm thinking is like, here's your potential question. So let's just do this as okay. So you can say yes question, no question, and then like up or down. Up question.
Yeah, this is like two different bases you're describing.
Yeah,
like
2 different bases, right? So now,
yes, no, right? by default it's like one basis. Maybe you have up and down, which is completely different.
Yeah.
But the representations can be different.
Mm-hmm.
But evolving those, it's like evolving these representations. It's like you don't change the yes and no. Change the.
Sorry, what were you saying? Yeah.
You're changing the vectors that you encoded these outcomes with, in a way. Right? So that you can be biased towards one or another. Maybe if they are not orthogonal at some point.
So this is what I was thinking, right? So let's say you have a result here, but you decide to only ask this kind of question. Okay. So what happens is, So what happens is this thing collapses if you only asking like these possible outcomes. So yes or no is like kind of observable, but you've evolved this into saying like it's like
I kind of assume the problem here. You assume that asking down is just what you can ask on its own. Usually, there's already yes or no. It's a single question. It's a binary question. You can't just take half of it. Like you took just the question down. Is it down? By itself, it doesn't have a meaning. It only
you could
has
say,
a meaning.
What if you just, I mean, what I'm saying is like, what if you change this question to say like, yes or no, or up and down? So it's up and down, yes, like as.
Yes, yeah, you can combine it.
That's what I'm saying. So you're kind of like you're combining them, but this is what's changing is like what questions you decide to ask is the evolution. So you're doing this one, or let's say this one. That's the thing. It's like, and then again, that ties you back into this like mixed state kind of situation where you have like 4 or whatever potential whatevers, and then you combining it here. So by combining, you have negative probabilities. Okay, well, my analogy is a bit wrong in this case, but or it's like it's a bit confusing. But so can you evolve the questions? Like, does what questions you ask give you the Heisenberg interpretation of quantum mechanics?
Yeah, in a way, yeah, I think so. It's a questions or a basis. You either change your question or change your basis. It's
okay.
For the more technical analogy, it's like evolving covariant and contravariant tensors. They have all forms or whatever. You have 2 different ways of transformations.
Mm-hmm.
You usually have it in special general relativity. That's the usual way of speaking of covariant versus contravariant types of quantities that can be differently transformed. Using there, you usually use Lorentz transformation, but it's still a linear transformation, which the same kind of analogy applies here when you also have a basis. And you can either change your state, which would become basically a state is a contravariant because it changed contrary to the change of basis. But an observable would be a covariant quantity because it changes in covariantly with the change itself. So it's the same way. So the changing basis and changing an observable is the same thing because they covariantly change. So that would make an observable a covariant quantity. I think it makes sense. Yeah, I never thought about this way before. Just this.
It makes sense. So okay, so let's think of a valid example. So if we use the cat in the boxes example, if we use Schrödinger's cat example, and we put into this, like we'd have to evolve the basis. So in the Schrödinger's cat example or thought experiment, what is the basis? Dead or alive? Decayed or not decayed? Does it have to be all 4? Decayed, not decayed, dead or alive, or is it just a 2? Can you have a quantum state with just a basis of 2?
If they in the sequence, you basically change the basis. If you start with the particle decay or not decayed basis, right? Then it hits some other bunch of operators that at the end it just changes the basis to cat. whether it's dead or alive.
Okay.
So somewhere in the process, this basis changed, but it can't be quantitatively represented by the same one, right? Because it's still binary, it kind of makes sense to have the same representation.
Yeah, sure.
Maybe you can change the labels if you wish, like we did here. You change the cat label. You could have changed cat to actual atom decaying.
Sure, my
But
question
the representation should stay the same.
Okay.
Yeah.
So but the question is, can you have a quantum state with just a single basis pair? That's not possible, right? It has to be
Single. Well, it's one. You mean it would be one-dimensional then?
Yeah. So you can do that?
One-dimensional is like, no, technically yes, but it's not very useful. It's like there's no ambiguity. It's just a single
There's no
outcome.
ambiguity. Okay.
You can even have a 0, 1. Zero-dimensional thing just always become. It makes everything impossible. It's like there's no outcomes.
Okay. So what is the in the Schrödinger's cat example, what are all the basis pairs? Because we're changing the basis during the experiment, but is it still just a single pair?
No, because it's a single system, kind of. It's a single wire, just evolving in time. So yes, it can be represented as just changing
very
basis.
Simple. Okay, so it's a very simple.
There's no like correlation to some other thing.
Yeah.
To some other system, just one.
There's no correlation to some other system, so it's like it's not as weird as it could be. Basically, is what we're trying to say. So how would you? So what would changing the basis look like here? So if we're saying the cat's dead or alive, you're changing the question to saying, is there a cat? We're not asking whether it's alive or dead. Or we're asking, is there something alive or dead? But we don't know if it's a cat. So you open the box, you don't know if it's a cat or not, and it's either alive or dead, or you open the box and there's definitely a cat, but you don't know if it's alive or dead. So there's a quantum state of questions that you could ask.
Sure. You're observable at the end asking about the cat, right?
Yes.
If you evolve backwards in one step where the atom was decaying, you effectively change the question.
Yes.
Right? Without changing anything else. You just change the labels in this case, right? You just apply the identity, essentially. Just change the label from the cat to the decaying part. But then the actual decaying happens. That's your initial state. It's already in superposition, so there's no operator there happening. So maybe that's what we're trying to make here was kind of wrong. Because there is no actual operator that turns your atom to the atom that is in superposition, unless it was already in one. In this particular scenario, unless you can construct one that turns a stable atom into one in superposition, then we can apply something. So in this case, maybe Schrödinger cat scenario is not very interesting even in the Heisenberg picture, because there is no action of operator anywhere, just change of labels. You need some operation that actually changes the state or observable from like in this case from stable to the one that is in superposition. Yeah. Well, imagine that there is such an operation that you can actually activate your uranium atom, right? Or something like that. Then asking it from the backwards observer perspective, that would mean that the question changes from whether it's a atom decayed or not to just what would be it's like it should be the orthogonal question to that.
How about this? Okay, you're an observer, you're going along, you see a box lying on the road. Okay, You open the box, there's a dead cat. Suddenly it's like, why is the cat dead? Becomes your question. But if the cat was alive, it'll be like, why is there a cat in the box? Okay, becomes the question. So depending on the observation, your question changes.
It's not very binary question then, right?
No, it's not, but that's the point, right? There's a superposition of questions you could ask. You should be asking, if the cat's dead, you should also be asking, why was there a cat in the box? But that's not the question you asked. The question you asked, because the uranium atom did decay, is why is the cat dead? So the uranium atom decaying affects the observables from the perspective of the observer.
Uh-huh. Yeah. Maybe there's like another easier scenario where there is not an atom decaying, but maybe we just take the actual polarization or spin in consideration. It's like the actual trigger of the killing the cat is whether you're spin up or spin down. Right? Okay. So that there's some actual sense to make an orthogonal question to that. Because instead of asking whether it's spin up or spin down, you can ask whether it's left or right. Yes, so that's how the question evolves. Maybe with the decaying, it's not so obvious.
Yeah, it's a bit complicated. Yeah. So there's an orthogonal question, which
so it's kind of where it becomes very stupid, because if your actual system was either spin or down, spin up or spin down, asking it whether it's left or right, so it's always going to produce a 50-50 chance. So it's like you turn it into a superposition, essentially. Your question is so ambiguous. So
there we go. Okay, that's a perfect example of how evolving the observables creates a quantum state, right?
Yes, the superposition.
Superposition.
Well, it's in a way it's always in superposition. It was in the beginning in superposition, like the state itself. Or maybe, it could have been. No, it's fine.
We'll say the particle's not a quantum particles. Let's say it's some kind of like normal thing, right? But by asking the question, you've created a quantum superposition. By asking asking a question that can put it into a superposition, something like that. Because the superposition is of the spin, but if let's say it's just a like something simple, like a coin flip. There we go. Let's say a coin got flipped, and then the question, you change the question. You say like, what was how many times did it's like you could ask any orthogonal question that doesn't make sense for the observation. You put the state of the coin flipping into It's like saying, is the coin on its edge or is it lying flat? That's the question. You don't observe whether it's heads or tails. It is definitely heads or it is definitely tails. But by asking the question, is it like on the side or is it flat? You've answered that question, but the heads or tailsness of the coin has become a quantum superposition.
Yeah. Maybe the problem is also here that we're trying to make qubit or spin particle into two-dimensional question, even though it's already clear that it has 3 degrees of freedom. Maybe that's why you have to have this notion of conjugate pairs like we had here, so that you also have some orthogonality, so that you even have this potential to have a superposition. So a coin is not enough to make a qubit, or because there's no sensible orthogonal question to it. You have to make isn't
that an orthogonal question? Because sometimes the coin can land on the side.
It's kind of, but that will technically make a 3-dimensional now probability distribution.
3-dimensional.
That's better. That's better, but if you have a 4-dimensional one, when you can separate it in nice pairs. When you have when your dimension is a perfect square, and like a tetrahedral dice would be perfect to represent a qubit.
Tetrahedral dice.
Yeah,
that's cool. I haven't seen one of those. Maybe I should get one. There's this game shop. I actually bought this dice at the game shop recently, so it's like good for neurodivergence. But they've got like all these different types of dice you can get. I'm gonna see if they have a tetrahedral one. Actually, that was my my question. Was did you... Okay, there we go. That's the meme. Okay, nice. Please post that on the community Discord. I really like that. So my question is, have you made progress on your quantum state qubit position inside a tetrahedral block sphere picture yet?
No, it's kind of was complicated.
Okay.
I can try to explain it because I have some nice pictures. Let me.
Okay, I'm gonna read the chat so long. Okay, so I am Poop asked, space-time could be an observable, right?
Well, because position is kind of already an observable. There are some problems with time, but yeah.
Could the box be space-time in this cat analogy? Right. The cat analogy is a bit tricky. The Schrödinger's cat box is a bit tricky because it's like you have these label changes and stuff. But yeah, of course, space-time could be an observable. I guess would it be a superposition between space and time? Like you can't measure time perfectly and space perfectly at the same time. Something like that.
Well, there are a bunch of like questions you can ask. Yeah, people certainly try to quantize the metric from general relativity to make something like that.
Yeah.
Right. So, yeah.
That's what they were saying. Like when you try to measure something too definitely, your measuring device ends up being so small that it becomes like less than the Planck scale or something, and then like at some point your measuring device basically becomes a black hole, and then that like makes it impossible to measure your location over time with arbitrary precision. Do you know about that thing? There's this famous scientist that.
Well, you can. By the way, you cannot think of this capacities and flows. They kind of can be interpreted as wormholes in some way, because you have this ER equals EPR conjecture. The entanglement is the same as a wormhole. So the same kind of configuration of space-time. The solution to the Einstein equation is the same as having an entanglement. I think it's still a conjecture. but
is that conjecture giving you quantum mechanics from general relativity? Is that the idea of that conjecture?
I think it's other way around.
So you're quantizing like gravity.
Space. No, you're not. In a way you create space-time from entanglement. You're kind of knitting them together. You knit together the space-time using entanglement.
Yes. Okay.
So that's essentially your fibers or whatever it is that become the structure of space-time.
So wouldn't that be closer to like the Wolfram Physics Project narrative for it, or not yet? Are we not?
It is close, yeah.
Yeah, it's closer, right? Yeah.
That's why I said you can think of it as something, as a part of the hypergraph that you evolve. And that's then become a space-time, the evolution, and knit the space-time together. That become the structure of space-time.
Okay, sorry, go back to your picture there that you opened in another notebook. That looked really interesting. Yeah.
So I was trying to, what essentially I was trying to do is to make Hilbert space turn it into a Euclidean space just for qubit, because you have a in a particular sense that you interpret the probabilities of measuring a qubit in that specific complete basis of 4 projective measurements that can completely describe the qubit state, the qubit density matrix, as these 4 symmetrical regions of the ball. It doesn't have to be a ball, it can also be a tetrahedron. But the thing that there's like, you can separate it in 4 regions, right? They're identical, and then you can imagine some object. It's like I drawn here as like another tetrahedron but you can imagine that there's some other object, maybe another ball that's just sloshing around with that phase space and overlapping. Because I think of this 4 regions as some actual coarse graining of the phase space, right? This is like mostly fine grained, the maximal fine grained phase space of the qubit, because it's 3 degrees of freedom. So maximally, what you can do is to divide it into 4 regions because of like a probability vector, because the fourth probability being the fourth just can be derived from probabilities being in the other 3s. So 3 degrees of freedom is the same as dividing 4 regions. That's all I'm saying.
Wait, I don't get that part. Why is it not why are you not dividing it?
Probability vector has to sum up to 1, right?
Yeah.
So if I give you 3 probabilities out of 4, you can compute the 4th. So it's 3 degrees of freedom.
Okay.
So
3 degrees of freedom can give you, okay.
Yeah, so if I give you the overlap of the particle or the object and what would be the volume overlap with 3 regions, you can compute the percentage of overlapping with the 4th region.
Sure, okay.
So it's kind of, this picture has 3 degrees of freedom in this overlap sense.
And is it 3 degrees of freedom because it's a tetrahedron in the middle there?
No.
If it was a square, would it be 4 degrees?
No, it's because of the 3 degrees of freedom is the 4 regions. The object inside doesn't have the only purpose for the object inside is to determine the proportions, so different possible proportions with these 4 regions, right? It's like it could be another ball. You throw it in this phase space. You compute the overlap with these 4 regions. Those determine the probabilities. They give you the probability vector, the 4-dimensional, and that's exactly the same number of degrees of freedom that you can describe your qubit with. So that's like, this is like a physical description or the physical phase space of the qubit. The analogous one. It's like, instead of describing more concretely, it's like we had this. There's like a special tetrahedron projective measurement, projective positive operator valued measurement that you can measure your qubit with. It gives you 4 probabilities, right? So those probabilities describe the whole density matrix completely. This is like the same as these 4 different labels on the transition graph, on 4 capacitors, which also have 4 values, right? So the same kind of thing. So, but this one can be interpreted as volumes, which is also how the classical statistical phase space is interpreted, as some kind of volumes when the particles leave, right? But there you have the volume between like delta x times delta p coordinate momentum boxes of h, of size h.
Okay.
Q, right? Here is just like the phase space of internal degrees of freedom, which has just 4 different boxes that whatever your tetrahedral can occupy.
Internal degrees of freedom. Okay, that makes sense. Okay.
So different locations of the tetrahedron inside this ball produces different probabilities and describe this quantum state. So it's like a physical phase space. It's Euclidean because now you describe it not just some abstract block vector in some abstract Hilbert space or whatever it is. You describe it like in this Euclidean sense as position of this tetrahedron with this ball, and then the probability is determined by just the ratio of volumes, how much volume it occupied.
Okay, hold on. So it's 1, 2, 3, 4. Wait, 1, 2, 3, 4. Okay. So in the middle, you're kind of forming a tetrahedron at the intersection of the four spaces. Is that the right way to describe it?
Look, let me show you this example. I think it's clear. It's like you can put your tetrahedral just on the apex, or whatever you can imagine as a ball. The point is that it doesn't intersect one of the region at all.
Yeah,
right? It
but
doesn't
the corners of the tetrahedron point to each vertex on the outside of the ball.
Well,
if it was in the middle.
Well, yeah. No, it doesn't. It doesn't. In this case, it matters. The only thing it matters how much volume it like is contained within those regions, and there is an equal amount. So it's basically 1/3 in each.
Yes, one.
So the probability distribution is like 0, 1/3, 1/3, 1/3.
Yes,
that's the vector.
Yes.
And that corresponds to the quantum state 1.
Okay.
That's the probability.
Okay. So I think I just figured out a way to visually describe why there's only 3 degrees of freedom. Because if you have your, wait, let me just draw here. So if you have your ball like this, where the vertices of the intersections between the 4 spaces are, forms a tetrahedron. Right. So this is red. So like the internal degrees of freedom are always going to form a tetrahedron on a ball that has 4 states on it. Something like that.
Well, doing 4 states.
Outside, like there's 4 colors on the outside of this ball.
Yeah. Well, so, first think of those as macro states, I guess. But
macro states, yeah. So
sub macro states. It's like in usual statistical physics, there's like some multiplicity of microstates. It's like how many microstates each, like how many configurations of particles can make the same microstate. That's good.
Can make the same macro state.
The same microstate. The same microstate has some multiplicity because a lot of configurations can make this microstate, right? So that's what is then connected to entropy, right? That's what the Boltzmann entropy is. It's basically how many microstates form a single macrostate. Right? It's just the particular configuration. It's whatever system your macrostate is in now, its multiplicity is the entropy, so it's logarithm. Right?
The multiplicity of the microstates. The possible
that
microstates.
This particular macrostate that the system is in.
Yes.
Because you don't know, like this, it's like you don't see, you have uncertainty about it. You're missing the information of an exact microstate, the configuration of particles. Because they can be in any microstate. So this is like a very discrete system. It has 4 possible macrostates, right? But because it's a quantum particle, it can occupy multiple macrostates at the same time, right? And that's the difference with the classical sense. In the classical case, when the particles, there is only a single microstate. So here it's overlaps. It's the same as saying as in classical phase space, your system is only like in a single point, right? Or spread out when you assign some probabilities, because also in the classical sense, you can have density of your state because you have some classical uncertainty about it, but it's still the same macrostate. Right?
From an observable that doesn't care about, from observable, it's only asking questions about the macrostate. There's only one microstate.
Yeah. Well, there's not one. It's just in this particular at the same time, right?
They're all okay.
It can still evolve, right, and change macrostates. You can like have volume change. You have energy, temperature change. Number of particles can change, but the point is that's the macro. That's what forms the macrostate. The statistical physics and classical thermodynamics. In this case, it's just a single qubit. It's just already a single particle. But kind of zooming in on this one region of classical phase space where this particular particle lives, and just focus on its internal degrees of freedom. And if it's a spin 1/2 particle or qubit, because we don't care about you have this this difference. Its internal phase space has 4 macrostates in total, right?
Yeah.
And it kind of occupies all of them, or multiple of them at the same time. It's like it can maximally leave one of them out.
Yeah, maximally. Yeah, but it's impossible to leave more. Wait.
No, you can't zero more than one.
Yeah.
You can't completely zero out. But yeah.
So there is a microstate that allows it to be only one macrostate, right? If you put the tetrahedron just into the green.
Being in one microstate is like being a completely determinate.
Yeah, there's only one potential microstate that gives you. In other words, the tetrahedron. There's only one exact position the tetrahedron can fit in, where it's only being one color. Like if you squeeze that,
well, even that you
tetrahedron.
can't. It's like this is like a cartoon that you still have to constrain the movement of this tetrahedron. You can't really. It's like you can technically put it here.
Yes, that's
right?
what I'm saying.
You can't. There's actually some constraint to how it's moved.
Oh, why? What's constraining it?
Well, constraining the actual representation. It's like I have the technical basis that I'm measuring in, right? And I know the region that the actual in probability space, what kind of probabilities are possible if I measure it. And that's all we can do there is I can only zero a single one. And those would correspond, it's like on the block sphere here, right? If your qubit is just arbitrary point in there, those vertices of this tetrahedron actually show those different questions that you ask of the state. That's exactly correspond to probabilities of whether you ask whether it's here, 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 or here.
Okay.
Right. It's like a So if you project your qubit to all of those 4 different locations, it describes the qubit completely. Right. So it's just encodes the density matrix in this maximal symmetric way. That's why it's called SIC. S stands for symmetric. So we have this 4 pure states that you can project your arbitrary state to, and the probabilities encodes the quantum states. It's like gives you the information about quantum state. But obviously, it's like if you imagine arbitrary vectors here, there's only a single vector that has 0 for one of them. It's like that's the vector that points to that particular one. Like this 0 one. No, actually, the reverse of that. Like this one.
Yeah.
Would give you 0.
Wait, no, but that's 6. 1, 2, 3, 4, 5, 6. Because there's left and right here as well, right? So shouldn't that be 6?
No, that's the axis of the block sphere. That's just those are different sets of measurements. Those 6 one there.
Okay, interesting. Okay, I get it. I get it. Okay. That's your entire set of probabilities. Combination of probabilities. Okay, got it. So how is this different to the picture just above it?
Well, this is like a picture for the Hilbert space, right?
The Hilbert space, okay.
Yeah, so like if you plot our vector here, it just has some actual location in this block sphere, but I want to recover the same probabilities, right? Of instead of being a vector, I want to recover them in the same way as we recover probabilities in the statistical physics by just how much volume is occupied of the phase space, but doing it for this internal representation. So we're trying to make, there's like a nice geometric basis, which is called tetrahedron, which like has this geometrical meaning. What if there's some dual notion of it, when instead of having this picture of projecting the state to those 4 vectors of the vertices, you instead try to encode it as a volume overlap. And what would that what requires mathematically to do it?
Okay, so
it seems like it's very non-linear. Yeah, it's like technically I think it can be done. It's going to be like a very ugly non-linear transformation. If you if you have a tetrahedron inside, at least.
Why is it
Actually showed
non-linear?
you. Well, just showed, for example, let me find. It's clear, for example, how to encode the one state, the one with the zero probability. It should be here, right? If when you put just this tetrahedral on the apex of that one. But the 0, 1 should be somewhere when you push this tetrahedral down to this yellow region a little bit, right? And I was computing this, how much you have to actually push it in order to recover the probabilities for the 0, 1. And the probabilities for the 0, 1 would look like this one, right? So it's for the yellow region, it would take exactly 1/2 of volume, right? So kind of very symmetrical one.
Exactly 1/2 of the volume of the tetrahedron.
Yeah, or whatever object it is. And I actually computed it. It took me too long. I actually computed how much you have to push this tetrahedral in order to, so that it exactly occupies 1/2. And there's a very ugly number. Let me get it. I have a picture for it. It's here. Or maybe this one. I think this one is the picture. So I was computing this actually. Oh no, this is for. Oh yeah, like this. Yeah.
Okay.
So I think this is exactly the half. I also have this picture, which is cross section. This one. So I was computing the volume of this guy. So it's so that it would exactly be half. How much you have to push. And it's not very ugly. So it's in this case, it's very clear how much you have to push it from the center. But it's like a completely different number in order to print. So it's not symmetrical. Let's say like 0 and 1 here. So the distances are different, so it moves non-linearly. But technically, you can solve for every state. Like you have to solve some complicated set of equations. I don't even know how to write yet. But you can just set up the problem. I give you these 4 numbers of how much this object overlaps, right, with these 4 regions. Compute me the actual center of that object. It seems like you can compute it because the all possible overlaps are possible, and I think it's even unique, right? But the actual shape of then you can even draw the shape of that all the states, and I think that would be also a nice picture. If I don't know. So I don't want to do it. It's too complicated, but I really want to see what the shape of that object is.
So it's going to look like a graph with 4 colors and then like 4 overlapping line graphs.
Well, I want, for example, like for every point on the sphere, right? I want to compute the position, the center of the tetrahedron here.
Yeah.
Right. So that the volumes will produce those probabilities, and I want the shape that the ball have in this case, and it's not going to be a ball, and it's not. It's going to be some weird, but should be symmetrical.
Oh, wait. So if you're saying just rotate this thing a little bit. I want to draw on here as well. Rotate a bit to the right. This the what do you call this ball, by the way? Have you got a name for it yet?
No. Well, give me a name.
Flux ball.
Yeah, if everything is going to be flux.
Because it looks like a flux ball, right? The flux capacitor looked like something like that. So now it's just a flux ball.
Yeah, well, maybe.
Okay, so here's my question, right? So you're saying the center of the tetrahedron for every position in the sphere, but every position in the sphere is going to occupy an internal sphere inside that sphere like that. Because when it gets to the edges, there's like a limit to how close the center of the tetrahedron can get to the edge of the sphere.
Yeah. Well, here, for example, you can't move the tetrahedron more up, right?
You can. There's still a bit of space here, right?
Well, that's because I chose this particular size. But I don't want also to move because that's maximally already the maximal state that you can go. So like I don't need to further reduce the distance from this region. So it seems it's already,
I see. Okay,
maximum.
So you could just shrink this here. Okay.
Yeah, the size of this object can be shrinked.
Okay.
In a sense, this particular size that I chose is arbitrary.
Okay. So actually, the size of the ball is the size of the sphere is something like that. Oh, it's arbitrary. Yeah, okay, so it doesn't matter. But so, are you saying the limitation is that the tetrahedron has to touch? It can't leave. It can't leave this the center of the sphere.
Yeah. Well, yes, from some symmetric considerations.
Okay.
That's the maximal state that represents the one.
The zero.
one
Okay.
No, that's the one. The one that when it sits on top, that's the one.
Okay. So what you're trying to calculate is what the shape
of the center of the tetrahedron or the ball. I also tried the ball. It's a bit harder to compute it by hand. I also showed if you actually take the maximal ball, right, in this region when it just sits on this apex. When you take the maximal ball size, when you push it maximally down, it's not enough to reproduce the 0, 1. It's like it's not. It's like not half of the volume, but 0.4 something. So we can have the maximal ball and push it maximally down so that it doesn't overshoot it and produce the same volume. So if it's a ball, it's also like with some radius that's smaller than the maximal one.
Yeah, sure. So I mean, wouldn't it just look like something like this, where you have every single position of the center of the tetrahedron in the sphere, and then you have like green doing that, and then you have like red doing that, and you have like blue doing that, right? Like maybe it's just like this. Wait. No, it can't be linear, right? You said it's non-linear. So it's like something like that.
When it's doing what? When you just change the state?
Moving the center of the tetrahedron to every single potential state inside the sphere. So this is volume, this is position.
Yeah. So that's one of the numerical methods you can, I guess, perform. You just choose the object, move it around, right? Draw these lines, and then when you given the actual numbers, you find the slice through this graph that you just draw. Yes. Find the slice, the slice that reproduces these numbers, and that's going to be the position. You find the slice.
Yeah.
The vertical one.
Oh, that gives you the probabilities then, doesn't it?
Yeah, the graph is already for probabilities.
Yeah.
The overlap.
Yeah.
How much volume, because proportions are the natural geometrical representation of probabilities.
Wait, so wouldn't the x-axis in that line, in that plot that I just drew, wouldn't the x-axis be the observables and the y-axis be the states?
No, states are already if states are this T1, T2, T3, those are different kind of questions. Those are the observables. The fact that you have 4 graphs, 4 different curves, those are kind of as an observables.
Those are the observables. Yeah. Okay, makes sense. Okay, I got some questions here. Could the yellow part of the ball be time and the rest of the colors represent the 3 dimensions of space?
Well, there's like a nice symmetry. Of course, I also noticed it, but like the fact that there are 4 probabilities, and the fact that there's like a 3 Pauli matrices and plus identity. There's all kind of there's like a very close analogies between space-time and the spin itself. That's why they always look alike. There's like other kind of geometrical theories about how to connect them. But yeah, there's always natural to assume that these 4 dimensions and 4 outcomes can somehow connect to space-time.
The fact that things are spinning makes stuff complicated, right? Because if nothing was spinning, then like everything would just collapse, and like time and like the future and like the past would like connect. But because it's spinning, you have the ability to travel in a part of a black hole that doesn't suck you into. You can pass the what's that like the outer limit of a black hole, and then like still not like go to the singularity if the black hole's spinning. Okay, sorry, I'm changing my topic here a little bit, but the concept of spinning is kind of deep. Okay, did you guys just realize, because this model has edges that you can slice a surface through and take flux, that you start with the phrase flux capacitor and figure out what that means mathematically? I'm gonna have to read that again. I don't know, Swish, can you read that comment in one go? Oh, okay. Quantum flux capacitor sounds like a Rick and Morty thing, not a real thing. Okay, you must be a millennial, because the flux capacitor is from Back to the Future. Actually, can we bring up a picture of the DeLorean? That was like the reason why this was a formative moment in time for us all. Memes might know what we're talking about, right? Back to the Future.
How do you spell DeLorean?
DeLorean. L-E-N. Actually, wait a minute. Wasn't that the bounty hunter from Star Wars was also DeLorean or something? Maybe I'm getting my sci-fi mixed up here. There you go. This was the dream car from the 80s.
Yeah, that's where the flux capacitor is.
Oh, it's in the car itself.
Yeah.
Yeah. Right. The car is the time machine.
Yep.
There we go. Okay, hopefully that cleared things up. So inside the flux capacitor sits a flux ball, and that's the Mandalorian. Sorry, okay. The Mandalorian, not the DeLorean. Okay. So there we go. So the flux ball is the mathematical representation for what happens inside a flux capacitor. Yeah. Okay, so phrased seriously, is this the actual name of the phenomena you're studying, or just a funny title for the stream? Okay, so they're asking about this. So a flux capacitor, I think it sounded very sci-fi back in the day when the movie was made. It's kind of, apparently there is a flux capacitor used for like some kind of electrical circuitry where you manage the flux of the circuits or something like that. But it was a free word to use at that stage. We're testing out the ability to have that word used to describe Nick's inventions.
It's a fun name for the stream.
Yeah.
Short. Yeah.
Clickbait, but maybe the clickbait turns into reality, because the kind of stuff Nick's doing here, like it's a novel conceptualization, right, Nick? There's not existing work done on this volumetric qubits.
Well, I couldn't find it. It's like I found a bunch of works on qubit geometry. They don't appear to have this particular one. No, or the answer to this question, whether anyone had it. I couldn't find it. If anyone finds it, please let me know.
Yeah. So if anyone on the stream manages to figure out if there's actual research on this, we could use it to get to these calculations a lot easier, maybe. Cool. Okay, thanks for that. That was a fun little trip into the future and back, I guess. Back to the Future. I guess it's interesting because the movie Back to the Future is actually in the past now, and we're in the future of a movie that we're talking about that was in the past.
Yeah.
So it's kind of
no
like
flying cars. No flying cars.
No hoverboards, unfortunately. Hoverboards were supposed to be here last year, I think, or the year before last. So sci-fi doesn't always make reality. It's funny how the field of science has quirky names from the last few years of it being studied, for sure. Okay, cool. Thanks for tuning in. Hopefully that was enjoyable. I learned a lot about Schrödinger's cat and observables, so that was useful for me. And yeah, so Monday we'll announce the new streams for what we're going to do there. And yeah, if you join the Discord, there's an announcements channel, and the announcements channel now has a bot. Actually, the Discord has a bot that we've named Ruli. So Ruli is the rewriting rule, and he's a bot that's going to help us to do a bit of community management. So yeah, we'll add some functionality in the future, and you can start interacting with it. But yeah, so if you see Ruli doing stuff, rewriting comments and doing some other rule-based activities, that's a potential mascot that we're thinking of playing with for the Wolfram Institute. Okay, cool. Thanks so much, Nick, and enjoy your weekend, everyone.